did almost start the lesson without recording. I apologize. You guys can thank Ava because she reminded me. All right, so here's what we got. We got a bridge on the wall. We decided that the weight of the ladder on the wall. We decided that the ladder is 22 pounds. We decided the person climbing up the ladder is 200 pounds, and we just decided that this angle is going to be 70 degrees. So the other thing I'm going to tell you is that the person that is climbing up, we're going to say, is about 30% up the ladder. Now, notice I didn't give you a distance. So the way that we would say that is from the bottom to roughly where they're at is 0.3 L. Where what does L probably stand for?
Meter.
The length of what?
The ladder.
Yeah, the length of the ladder itself. So I'm not going to write it up here, but well, I'll write it just briefly. So L is this. You do not have to write L. I just want you to know where L technically is. What's up?
Does that mean we can set the length of the ladder or no?
You could, but actually this is going to be, you're going to find this to be easier. You are right. You could put the length as anything. This could be an 8-foot, so this could be a 10-foot ladder. This could be a 20-foot ladder. 30% of the way up of a 10-foot ladder is 3 feet. 30% of the way up a 20-foot ladder is 6 feet. So technically in different spots. But the reason we don't need to know distances is because it's actually only percentages and ratios that we actually care about. And you'll see that later when we do the math here in just a second. Cool?
Uh-huh.
All right. Now, let's continue. I asked you to do force diagram yesterday. Let's talk about what that force diagram needs to, extended force diagram. What's that extended force diagram need to look like? Yes.
Force normal. Okay. When you say this, you mean on the ladder, right? Like.
Yes, we are talking about the ladder.
Force normal, like one up and one side.
Yeah, so there's 2 force normals, okay? What we call those is always up to you, but I am actually going to use particular things that your book and other problems regularly use, okay? That doesn't make them right. If you wanted to call them something different, that's completely fine. I'm going to wait on that until we knock out some of the easier ones here a little bit. Okay, but yes, those are definitely there. Yes.
Force gravity.
Force gravity, where does it go?
The center of the ladder.
Yeah, so if it's an 8-foot ladder, of course that'd be 4 feet up. If it's a 16-foot ladder, that'd be 8 feet up. You get the idea, but it's the center of the ladder. Now, sometimes people get confused on this, so let me make sure you get that. It's the center of this distance, definitely not this distance here, okay? Actually, it also correlates to that there, but here we go, right about in the middle. There is the force of gravity, okay? What other force should be on it? Force person, right. And remember, as we discussed previously, that is technically not gravity, but it should also be equal to gravity, yes? So force of person. Good. And now let's talk about those force normals, okay? Which way does force normal go? Correct, perpendicular. Now I stress that only to say that please keep in mind no matter what weird angle something's at, like if I throw that tennis ball over into the wall, directly into the wall, or if I toss it at an angle, or if I toss it from above or below, that none of that changes the direction of force normal, right? Force normal is actually electrons on the wall pushing electrons on the object, and that's why it's always going to be perpendicular. So even though this is at a weird angle, who cares what weird angle it's at, there should be a force normal here. Now, to separate them, since there are 2 force normals, you got the ground and you got the wall over here providing it. They're technically both force normals. Somebody last hour said, hey, why don't we call this force of ground? Well, you're going to see potentially the issue with doing that. So let's not call it force ground because I think that's going to be more confusing than helpful. We'll just go ahead and call this one on the ground force normal. And to separate it, rather than call that force normal up there, what should we probably call it? Force of wall, correct, and that's going to go that way. Now, I believe I said this yesterday, but just on the off chance I haven't, most of these problems will say the following phrase, which is going to matter here in just a second, and that is we're going to assume that the wall is frictionless and the ground is not. That is actually a decent approximation, and we can get into the weeds for those of you that really care a little bit later on, like what if it wasn't, like in real life, but let's talk about this for a second in terms of these guys right here. The 2 problems I've done in class, both the bunny problem and the and the bridge problem from yesterday, have always started the exact same way, in which I have, I'll get your question right after I finish this thought, we've always tried to sum the forces first, and then we've eventually gone, nah, I need to sum the torques. And what's been the problem with solving sum of forces?
2 unknowns.
2 unknowns. Now, what I would suggest, though, is make sure that you are actually looking at these problems, though, always starting with forces, because a lot of times you can knock out stuff that is way easier when you're try to start here, and then figure out that you can't, just like we always have. You'll see that here in just a second. Here's what we're trying to get. We are trying to figure out what is force normal, what is force wall, what is force friction. One of those three is going to be stupid easy to get right now, and I'm going to argue that myself and probably you can easily do that math in your head. Discuss in your group which of those three forces is very easy to calculate right now, and do the math in your head to figure out what it is. Discuss in your group. What's that? Oh, I'm sorry. Yeah, friction should go. Yeah. Actually, I forgot. Sorry. I'm so sorry. I missed that piece. Which way should friction go and why? Right. And where on the right? Like, where is it attached to? The ground. Right. Because I assume, yeah. Why is it to the right? Sure. So sum of forces have to be balanced. And then the other thing is just think of reality, right? If you put a ladder up where there wasn't friction, so like the iciest ice that has ever iced, what would you expect the ladder to do when anybody got on it? Specifically, it would go that way, right? It would go that way, so that's going to push it that particular direction right there. All right, so yes, here we go. We've got 5 forces: force of wall, force of gravity, force of person, force of friction, and force of normal. We know 2 of them, okay? This is just the weight of the ladder itself, which you could find very easily by standing with it on a scale or putting itself on a scale. And of course, this is the weight of the person, which you could also measure very easily with the scale. Now, we've said the person is 30% up the ladder, and the question is, what are these 3 right over here? And the question on the table was, one of those is very easy to get. Which one and why? Discuss that quickly with your group. We'll be right back in about 30 seconds to a minute. Go. I'm gonna get rid of person here just for the sake of, like, it's kind of messy right now, so it's still there in the form of the force, but. All right, what's the easy one to get? Absolutely, and do the math in your head real quick. What is it? 222 pounds. Yeah, what simple thing did we do to figure that out? Sum the forces in the y. And this is what I mean by saying I would still always start looking at a situation that you don't know by summing the forces. Because here, I'll do the math for you real quick. Here it is over here. Sum the forces in the y is equal to 0. Force normal is positive, minus force gravity, minus force of person. But of course, we know what those 2 are, so force of normal is just going to equal force of gravity plus force of person, which makes sense. The ground's going to push up as much as the person, and that ladder are pushing down. So, now that being said, we probably shouldn't put our final answer in pounds, so let's go ahead and do those conversions real quick. If you haven't yet already, go ahead and do those on your own. What'd you get for the weight? No, the weight. If I'm saying weight, I mean force. Remember, weight is force of gravity. 97.9. 97.9. Okay. And what is force of person? 890. Couple people can confirm. Yes. Cool. All right. So we should probably do this in newtons. Force of gravity is, as we said, 97.9 newtons plus 890 newtons. Wait. No. That's on me. So I'm going to round that to 3 sig figs and call that 988. So what's the main takeaway in this particular spot? Don't overcomplicate a problem, especially when you can look at it in your basics on the forces. Because here's the deal. We've been dealing with a lot of problems that are like a straight bridge and forces that go in wonky directions, okay? But if you look at this setup, it's actually not on purpose because, I mean, you did the force diagram. This is just the way these go. What you'll notice is that the ladder is at a wonky direction, but actually every single one of the forces is really already nicely along the y and along the x very cleanly. So we've knocked out force normal already. Can we do the same thing with force of wall? Why not?
We don't know force friction.
We don't know force friction. Right. So now, once we get force of wall, is force friction going to be stupid easy to get? Yeah, absolutely it is. As a matter of fact, a very typical ask on one of these questions is going to be something like, hey, if the ladder is about to slip, what is the coefficient of friction? Which makes it sound way more complicated than it actually is, because I'll point out a couple things. One, what type of friction is this, surface or air? Well, you get to the next question. Yes, it's surface. And static or kinetic? Static. And remember, static goes which way? The opposite of the way it wants to go. So this ladder wants to slide that way. That's why it's pulling the other way. And remember, static has a maximum. Within a range, it's just going to go more and more and more. But when it's at its maximum, beyond that, it's going to break, and it's not going to be static anymore. It's going to be kinetic, and that's going to fall down. But if it says, hey, it's at its maximum, it's about to fall over, what's its coefficient of friction? Just a reminder, coefficient of friction is just that right there. So what you're going to do is, of course, calculate all of these things exactly like we're doing right now, and just take one very simple step at the very end. Take this guy and this guy, plug them in there, and that'll tell you your coefficient of friction. Does that make sense? I'm not going to worry about it right now. Just a reminder for when that comes up on the homework. What's up?
How do we know which force normal to use? Like, because technically force wall is.
Well, okay, because if it's asking coefficient of friction, okay, technically the coefficient of friction on the wall is 0. Why? What did I say at the beginning? Yeah. So it would only be, it would be the technically there'd be a different coefficient of friction for the wall and the surface in reality. Okay, so what you would do if we did have friction up here on the wall is if you wanted to find this coefficient of friction, you compare those two, and if you want to find the coefficient of the ground, you compare these two. Does that make sense? That's another reason why I am actually calling this guy wall and calling this guy normal, to help you just kind of remind yourself of those particular things. All right, so we need to go get force of wall, and we can't sum the forces, so what are we probably going to do? Torques. What's the first thing we have to do before we sum torques? Fulcrum. Now, there are two options you can do, and there is definitely an easier one, and I would suggest we do the easier one. So, where are the two options of where you can put your fulcrum? Remember, we technically know force normal. We could put it at the bottom. We could put it actually at the top as well. The top is going to be tricky because if I put it at the top, both of these two guys actually have the option of doing torque. So we would have 3, 4 different torques in this particular case. Whereas if I put it down here at the bottom, what nice thing happens? 2 of those forces are now going to apply 0 torque due to having no lever on. Does that make sense? Okay, so see if you can't start the setup of that. I'm going to give you 2-3 minutes ahead of time with me here. I will tell you the challenging thing of this is definitely angle, but we can tackle that actually after setting up the problem. So if you're not sure where to start, we've placed your fulcrum, we've done your extended force diagram, you are right here right now. Sum of torques is equal to 0, and move from there. Also, anybody watching on the video, one of the reasons we were a little bit late starting this video is we talked about Six Flags. I'll talk to you about that probably tomorrow. Unless you're watching this in the future, or if you're not one of my students and you're watching this, then no, I'm not going to talk to you about Six Flags. I don't know who you are. That is a weird thing that's actually happened recently. I've started to have students that are not my students watching the video. I would like to believe that I can explain the problem decently well. They like that.
Why would we put it at the bottom of the ladder?
Because you measure the angle from the lever on.
Do what now?
Why would we put it at the bottom of the ladder if we had?
You're not actually measuring it from the
Because we
ground,
don't have
you're
force
measuring
friction
the
yet.
ladder. So there is an angle.
And even if we did have force friction, that makes for like 2 separate torques. Like both of those are potentially going to cause torque down. Yeah.
Do we know what the length of the ladder is?
We don't. We decided to call it just length L, whatever that length is.
Do we need it?
No. No. You'll see this. You'll see how that it develops a little bit later on. For right now, but this is extraordinarily similar for those of you that have started 8.3 or haven't got there yet. Basically, all of the problems on 8.3 are done with the idea of L and not with actual numbers. It's like you'll see distances listed as 0.2 L, 0.3 L, or I'll tell you what's eventually going to happen is that when we put up all of the lever arms, okay, every single one of them will contain an L. So what's L going to do? Cancel out. Yeah. And the reason that is because we care about percentages actually more than we actually care about the actual numbers themselves. All right, running through this, if you want to do it on your own, you could ignore me real quick, but I'm going to do the next step, and that is, what is the sum of torques? So I'm going to start down here. Does either normal or friction do any torque? Nope, because of where we put our fulcrum. Let's go to person, and the main thing I'm asking here is positive or negative on this torque. This would be negative, correct, clockwise. So, the negative torque of person. Gravity is going to be negative. Remember, if you're struggling with that, there would create a negative angle around the center. So, yep, negative gravity. And the wall, positive. And remember what we said the other day. If you get to the end of these and you've done all negatives or all positive, you know you've made a mistake. There's no possible way those could be a zero then. All right, you do not have to do this next step. I've talked about this a couple of times, but I know I'm looking for force of wall. Okay, that's the only unknown up here that has not canceled. And I know that's inside of there. So I'm going to do my algebra to isolate torque of wall. Technically, the next actual step is to plug all the individual equations in. But I'm just going to do that torque of wall and add both these guys on the other side. So that's just going to be is equal to torque of person plus torque of gravity. And again, I like that as well because I'll just remind you, what does that mean? Well, it means person and gravity are trying to make the ladder go this way. And the wall is trying to make the ladder go this way. And apparently they're counterbalancing each other, so they must be equal to one another. Our next actual step between these two is to take the individual torque and fill out the individual equation. What is the individual equation? I missed that. A little soft. What was that again? What's the equation? Lever arm, force, sine theta. Okay, now it's going to seem tedious here. Don't care. I don't care because it's going to be helpful. So here it is. It's the lever arm of wall times the force of wall times the sine theta of wall is equal to the lever arm of person, force of person times the sine theta of person, plus the lever arm of gravity times the force of gravity times the sine theta of gravity. And usually this is the spot where I start to go like, well, let's at least cancel the signs that cancel. Do any of the signs cancel? Nope. How come? Yep. Everything's at an angle, nothing's at 90 degrees. Now I'm going to take a quick aside over here on the left and talk about that angle real fast. And I'm just going to focus on the force of gravity because I think you're going to mostly get everything from there. When we talk about torque, where does your angle have to be measured? From the lever arm to the force, correct. Now, is that the angle that was given to you? No. Now, the nice thing about the angle that was given to you is you'll notice that if I kind of subscribe a triangle over top of it, how are those two related? Complementary is the word you're looking for, or all of it's got to add up to 180 degrees inside there. That guy is going to be at 90 degrees, so those two have to add up to 90. So since we said this is 70 and not 72, you're welcome, then what's the other angle? 20. So what angle should be 20 up here? Person and gravity should both be 20. That being said, the wall, should it be 20? There's two ways to see that it is also 70. Your first way is your basic geometric shapes. If I have two parallel lines, these are alternate interior lines, right? They're both with the horizontal, they're both 70. Or if you don't like that, here's your other way. You know that that's 20, right? So is that also 20? Yes. And if that's 90 degrees and that's 20, this extra bit over there has to also be 70. Correct. Math. What a tricky foe. All right, and I'm going to do algebra, and I'm going to cheat because I've got the giant board to cheat, so sorry you can't do this, but here we go. I wish you could do this on your page for your own sake. You can't. I can, so here we go. All right. So I'm going to take that piece right there, and I've got an extra G for some reason. I don't want that extra G. Okay, so the force of wall is equal to that whole mess divided by these two. And let's plug our numbers in. What is the lever arm of the person? 0.3 L. Not 0.3, 0.3 L. Okay, what's the force of the person? I think that's the weight of the thing. What is it? Is it 980? 890. I'm Lex Dixik sometimes. All right, we're Teeple Poo. All right, now, the angle for the person was 20 degrees, plus the lever arm for gravity. I didn't give you any other lever arms, but I feel like some of these should be pretty easy. What is it? Yeah, 0.5 L, halfway up the length. And what is force of gravity? 97.9. And what's the angle on that guy? 20. Divided by, what's the lever arm of the wall? Not quite. L, there it is. And what's the angle on this? 70. It would be nice if it was 20, because if it was 20, who the heck cares what the angle is at all? They'd cancel out anyway. And there are problems that actually do end up that way, like a seesaw, in case that comes up on your homework. But it doesn't, because they are different, so you do have to be careful. Now, technically, what happens to L here? Yeah, so the correct, if I was your math teacher, I would tell you the correct kind of clean way of doing it is doing what with L up top? Factoring out the L and then canceling them. But you see one is in every term. Since one is every term, I'm fine here in physics with you just doing that right there. And what do we get?
115.
115 is what I got.
I ran it a little different. I got 120.
Sometimes it's hard to say. I did get 115 with these numbers that are up here, but how did you round differently? In what way? 890 was 890.
Yeah, 97.9. I rounded to 98, and then I did everything when I did like sine and stuff to 10.
Gotcha.
10's place.
Okay. All right, so that's 115. That's the force of the wall. That's not a component. That's the actual force of the wall. Now, I come up here, and I recognize, all of that work, and I just knocked out the force of the wall. I still have force friction to do. But what's the nice thing about force friction? I do expect you to still show that work, okay? Even as simple as it is, and it's not going to take you long. Here is that work. Sum of forces in the x is equal to 0. What are the sum of forces in the x? Positive force friction minus force wall is 0. Therefore, force friction equals force wall, and therefore is equal to 115 newtons. And like I said, on your homework, if it asked you to find the coefficient of friction, you'd still want to do this so that you could then show, hey, that's just 115 divided by the earlier 988 right there, or roughly about 0.1. Now, most surfaces are definitely much higher than 0.1, so this ladder is probably not about ready to fall, which you would probably guess. If it was at 70 degrees, you would not expect it about ready to fall. Now, what would increase the necessary amount of force friction? A larger person would do it, sure, okay. I would also say moving up the ladder. Moving up the ladder is going to have them cause more torque, right? The further up, because the bigger lever arm, which would mean force wall is going to have to be bigger, and force wall being bigger is meaning force friction also has to be bigger, okay? What is probably the most, that's probably not going to do it, I would guess in this case. The most likely case of them falling over is somebody setting up a ladder, and I think I'm going to set this ladder up, but I hope that you kind of laugh a little bit at my setting up of this ladder like that. That's a terrible way to set up a ladder. Why? For two major reasons. One, it's not going to help you very much. You could probably stand and reach that particular area. That's not the purpose of a ladder. And two, is force of gravity going to cause a lot more torque in this case? Yeah, so that thing's probably not going to stay very, very still that particular way at all. All right, last thing to go over in the last 10 minutes is a very, very, very similar setup. But I'm going to show you something that's going to help you probably a little bit later on in the chapter that I think that we're about ready for. Here's what I want you to do. Okay, I want you to draw a force diagram of a person, just a person, leaning up against a wall. Here they are, attempting to, hold on, I'm going to lock this thing in place so I don't accidentally knock myself over. Here we go, a person leaning up against the side of the wall, and then draw the extended force diagram of that. Similar to before, you may make the assumption that the wall does not provide friction. Thank you. Look at those broad shoulders. The person's really been working out his traps. Look at him. Got that nice V in the back. Look at it. It's clean right there. All right, lean wall. All right. Also, just a heads up, you'll notice that I draw a lot of my pictures going to the right. It does not matter if you actually have the person being drawn. Oops. What's that now?
That trapezoidal.
Yeah, it's they've been hitting the gym. All right. Why did that? All right, I don't know. Okay. All right, let's force diagram here.
From the ground.
I mean, starting with friction is kind of a weird spot. Let's start with the easy one. Gravity. Where's it go? Slightly above the belly button. Assuming they are human. What else?
What's normal above the feet?
Yeah, we'll combine that together and say force normal. And actually, what does that mean about force normal relative to force gravity? That's always sort of been the case. Correct. What else?
Force wall.
Force wall. And force friction. As a matter of fact, this is 100% the exact same setup as the last example. The only thing is you don't have a tiny person crawling up, that particular person right there. So it's not the same as the last one. Yeah, what's on?
So there are two force normals?
Technically, I would say yes. A lot of times, like you can kind of see me doing this with my feet, like when you lean up against the wall. Actually, usually you kind of only stand on one, or even if you are on both feet, you're not really touching one very much at all. There's probably one exact spot for it. And we're just combining the two of them together in this particular case. So, the way I drew the picture, I should have probably drawn the picture a little bit more like this to make it a little bit more obvious, like where they've got their kind of like legs like together, right, like there, so that we can say it like that. But technically, you are correct, but we can make this approximation and it work. All right. So what did I want to talk about here? Well, okay, you got force normal, force gravity that are now back equal to each other. So if it's a 150-pound person, that's 150 pounds of force normal, convert to newtons, whatever. And just like before, force of wall and force friction are the same. Okay, so what do I want to discuss? Well, what I want to discuss is let's treat the person real quick here like they are just a stick for the sake of simplicity here. And I want to talk about this. I have not given you an angle yet. Obviously, I haven't given you anything like weights or forces or anything like that. But let's say I don't give you an angle at all in this particular setup. Or let's say this. Let's say you go to a lab. And there's a lab setup, and I say, hey, just lean yourself up against the wall, and I want you to calculate the force of wall. Now, certainly you could go measure angle, but there is actually an easier thing to measure when you look at this setup. When we've been doing problems, if I said, hey, here's a lever arm, and here's a force, okay, you can, all right, great, it's 90 degrees. If I then say, hey, here's the force, you've been getting the angle so that you can calculate how much force is perpendicular to the lever arm. Yes? But here's the deal. We actually don't need the force to be perpendicular to the lever arm. We just need both of them to be perpendicular to each other. Meaning, you could either get how much force is perpendicular to the lever arm, or you can try to figure out how much of the lever arm is perpendicular to force. Now, am I really moving the lever arm? No, absolutely not. Okay, am I technically calculating the same thing? Yes. What's the nice thing about calculating it this way? Well, if I lean up against the wall over here, to figure this out, how much torque the wall is causing, you could either measure the angle between my legs, which you can sort of see that's not super easy to figure out exactly where the angle is, and not a complicated thing, or what is our perpendicular here in this setup? The distance from the ground to my shoulder. Not from my feet to the shoulder, from the ground to my shoulder. Is that going to be pretty easy to measure? Yeah. Yes. Yes, it is. So basically, I know the lever arm is R, but as long as I get this and it's perpendicular to force, I don't have to get how much force is perpendicular to lever arm. Does that make sense-ish? Yeah. Okay, so when am I going to know to use this? Well, in a very specific, oddly specific way. Let's say theoretically there was a horse that was leaning up against a wall. And on that wall, it told you some weird distances. Like it straight up told you this distance right there. What is that distance? That would be the lever arm for force of wall. What would the lever arm be that's perpendicular to gravity? Assuming, by the way, that the fulcrum is right down here at the feet. What would the lever arm need to be for gravity? What's that? Nope. Yes, the lever arm would be this right here. Why not this one? That's parallel, right. So the first one, if it makes it easier for you to see, is this right here. The amount of lever arm that's perpendicular to force. And if I measure that very nicely, do I need to worry too much about the angle? What's the angle now? 90 degrees because of where I measured the lever arm. Yes?
So you don't have to do sine theta in your like.
Well, you technically do, but
it's like
the angle's 90, so it's, yeah. So this goes back to something that I did early on, but I kind of like pushed you away from for sake of like some people screwed this up. I told you at the beginning that the torque is equal to lever arm times force times sine theta. And then I also told you that the purpose of doing sine theta is to make sure they're perpendicular to each other. Yes? I then told you another equation that I'm going to be fine with you going back to, and it's this. Torque is lever arm perpendicular to force. Now, when I wrote that the first time, I think some people thought what I was saying is this little symbol is making sure those are perpendicular to each other. Actually not. That little guy is a subscript of that right there. The lever arm that is perpendicular times the amount of force. In other words, if I have a lever arm like this, and I have a force like this, okay, in that particular way, this equation right up here, I could take R, plug it in here, I could take F, plug it in there, I could take that angle, plug it in there, and get it. Or I could measure this, the amount of lever arm that is perpendicular to force, and straight up use this guy and it will end the exact same way. If you're struggling with that, it's only for one problem. It's a later problem, but I did want to talk about it now.